Hello everyone, I'm Nayan. In this video, my teammates Heejoo and Manisha will be talking about a project DANCE, which stands for Distributed Advanced Neat Coherence Extension. Here's the outline for the presentation. In modern multiprocessor systems, coherent distributed shared memory is an appealing choice. Each processor has its private cache and local memory. These systems, often weakly ordered for better performance, rely on explicit synchronization operations to achieve sequential consistency. While MESI is a common cache coherence protocol in multi-core processors, it introduces an overhead and complexity impacting performance and energy efficiency, especially in scenarios with fault sharing. A recent shift towards data race-free programming model has diminished the need for strong cache coherence protocols like MESI. This project introduces a low-complexity cache coherence protocol tailored for distributed shared memory systems in data race-free programming. Some background about the project. Discussing data race-free further, they occur when multiple cores concurrently access shared data without proper synchronization, with at least one of the accesses being a write operation. To prevent data races, synchronization operations between conflicting accesses are crucial. For instance, Decker's algorithm can achieve this in a sequentially consistent system, but it isn't effective for weakly ordered systems such as like ours. In such systems, developers must implement hardware-recognizable synchronization mechanisms like locks or atomic operations to ensure safe modifications of shared data by multiple cores concurrently. The accompanying figure here illustrates a data race-free code using locks. In this code, variables y and z within the critical sections are safeguarded by locks, ensuring a certain order for writes to these shared variables. Self-invalidation is a simple cache coherence protocol that leverages the DRF assumptions that we just talked about to utilize synchronization semantics for cache coherence enforcement. In this conservative approach of self-invalidation, it invalidates all cache lines at synchronization acquisition and writes back all dirty cache lines at synchronization release points. It guarantees that every read within the critical section accesses the most current data, but despite its low complexity, self-invalidation exhibits high overhead at synchronization points due to unnecessary invalidations and writebacks. Neat serves as an instance of a low-complexity self-invalidation cache coherence protocol. With the Neat, self-invalidation is limited to specific critical section data, deviating from the conventional approach of invalidating all data during synchronization. It eliminates both the directory and MESI protocol, choosing to write back all dirty data during releases. While Neat exhibits comparable performance to MESI, its design is tailored for systems featuring multi-cores with single shared last-level cache, limiting its applicability. DANCE extends the Neat coherence protocol with modifications to offer support for distributed shared memory systems.
Okay, so let's discuss about DANCE architecture. DANCE suggests a hardware solution for distributed systems that has a low complexity coherence protocol, lesser false self-invalidations, and reduced risk of deadlocks. DANCE also introduces a new locking mechanism that decreases network traffic related to locks. Furthermore, DANCE also adds support for fault sharing, which usually occurs when multiple cores are actually writing on different offsets of the same cache line. So the system for DANCE looks as shown in the figure. It has a core, NIC, and a DRAM. Each core has an L1 cache, and each tag in the L1 cache has additional bits called stale bit and forward dirty bits. There's also a log station that keeps track of all the logs that are currently held by the core, and it stores some log-related information like signatures, bit vector, etc. in it. So the core can handle core can hold multiple logs at the same time because we support nested logs. A log manager is present in NIC of each of the node, and it is used in log management, which is later explained by Heejoo. So there are in the DANCE coherence protocol, there are three states in which the cache controller would be in. One is lock acquire, normal execution, and a lock release state. Upon successfully acquiring a lock, the system transitions to lock acquire state. In this state, it sets the stale bits of all the cache lines and then reverts to the normal execution state. After completing the critical section, the system moves to the lock release state. In lock release state, the cache controller initiates writebacks of all the cache lines modified in the critical section, awaits their completion, and then performs lock release just before exiting the lock release state. So subsequently, it then again returns back to the normal execution state. So we can see that the state transitions occur only at the synchronization points, like lock acquire or lock release. So when a core enters lock acquire state, it sets the stale bits of all the cache lines to 1. They are made to 0 only when the cache lines are self-invalidated and brought again from the memory. So as shown in the table here, if a cache line is invalid, all reads and writes will be misses. So has to bring data from memory. If the cache line is valid and not stale, then all loads and stores would be a hit. If cache line is valid but stale, then the writes can be served directly. Reads can also be served directly if we are reading a dirty word, but reads will end up being a miss if we are reading a clean word, because there's a possibility that it could be stale. And the other codes might have written to it. So we self-invalidate and bring the data back from memory. However, there's a catch here. What if no other codes made any updates to this clean word? Then ideally, we wouldn't have had to invalidate this cache line, but we end up self-invalidating it in Dan's baseline protocol. So to currently identify a real stale cache line, we use two Perlock based write signatures. One is the previous writer signature and the other is the Bloom filter based signature. So the goal of using the previous writer signature is it keeps track of the latest code that has made any changes in the critical section. While releasing a log, if code has made any writes in the critical section, it would update the previous writer signature and send to the log manager, send the signature to the log manager or the next code which is supposed to hold the log. So in a log acquired state would set the stale bits to 1 when entering the critical section, only if the signature doesn't match with its own ID. Okay, so this write signature, however, captures write information only at the granularity of the whole critical section. So its effectiveness is kind of limited. So we also use a different signature called Bloom filter based write signature. This is based on Bloom filters, which are probabilistic. So they are same as hashing, but they have multiple hash functions. So we use this feature of Bloom filters to capture addresses of writes made in critical section and encode them into a single signature, which can later be used to check if a particular address has been modified by any other code. So this way we can, by doing this check, we can limit the number of self-invalidations that we do while executing a critical section. So this is useful, but since Bloom filters are probabilistic and the signature length is limited, we would end up seeing some false positives, which basically lead to false self-invalidations.
Now we're gonna talk about log management system in our dense architecture. In the dense architecture, logs are essential for running DIF semantics, and they are distributed across the nodes and managed by the special hardware called the log manager. The log manager will reside in NIC for each node. The log manager maintains 2 write signatures and a wait peak vector for each log in its fixed size memory. Also, the log manager will communicate with the node cores through message passing mechanism for the log operations. The log manager's memory will be mapped to the physical address space for unique log identification during the message passing. In this slide, we will show how our log system works with multiple log acquisition requests. When the core 1 wants to go in a critical section, the log acquisition is initiated by sending log acquire message to the log manager. The log acquire message will include the core ID and the log address it is requesting. If the log is free with a log value of 0, the log manager will reply with the grant message after updating the log value to 1. With the log, the 2 write signature values and the wait peak vector information will be sent and saved at the log list station of the core 1. While core 1 is executing critical section with holding the log, core 2 can send the log acquire message to the log manager. Since the log is not available, the log manager will put the core 2's request to the wait peak vector, setting the bit 2 as 1, indicating core 2 is waiting on the log. And log manager will reply NAC message to the core 2, and core 2 will go on a sleep after receiving the NAC, so that it won't have to wait. It won't have to do the busy waiting. Following the core 2, the core 3 can also request for a log. For the log, the log manager will do the same thing as it did for the log 2's request. It will update a bit vector and then reply NAC to the core 3. Later on, core 1 finishes executing the critical section and will release the log. Since the core 1 saved the bit vector value of 0, it will determine there is no pending request and will release the log to the log manager. Upon receiving the log release message, the log manager will check if there's any pending requests on their side. Since the wait bit vector is non-zero, the manager will use the round robin scheme to determine the next granting core. It will start searching from the core ID bits next to the recently released core. In this case, the core 2 will get the next grant. The log manager will send the log grant message with the current wave peak vector information, and core 2 will save the log information in its log list station. The log manager will clear out its peak vector after giving the grant. This is okay because we will ensure the next log grant is given by the core 2 when it releases it. With clearing of the big vector, the log manager will only keep track of any new requests coming in after. After the grant, core 2 executes the critical section. When it finishes the critical section, it will release the log, but this time the core 2 will see the non-zero value for the weight vector. Then the core will clear its bit from the weight vector and will find the next core to give the grant in the round robin scheme, which will be core 3. Core 2 will send the core 3 the grant message with the log value and the bit vector. The core 3 will save the log information and execute the critical section. On releasing, core 3 will clear out its bit from the bit vector. After that, it will release a log to the log manager since there is no more pending request of the log. When receiving the log release message, the manager will check if there's more log requests of their bit vector. Since there is no more, the log manager updates the log value to 0, indicating the log is free. This method of offloading log transfer tasks from the log manager to the log holding core reduces the number of network messages involved in releasing and granting logs and reduces our workload of log manager for the log arbitration.
We assess the performance of dance in comparison to Messi through specific example scenarios. Consider the scenario outlined here. Address A is read by multiple cores, each bringing it into their respective cache lines. Subsequently, core 1 acquires the log and performs a store to address A. In the Messi protocol, a get permission would be required, prompting the home side to check for other sharers, core 2, 3, and 4, and send invalidations to them. Permission is granted to core 1 only after receiving all invalidation acknowledgements from core 2, 3, and 4. This writer-initiated invalidation process results in multiple network requests and heightened latency. However, dance avoids such invalidations. Upon encountering the address, dance identifies it as a cache hit, executes the write in its cache, and proceeds to the next instruction. This leads to a quicker processing of cache writes. In dance, the self-invalidation of a cache line A in other cores occurs only when those cores perform a cache read to that specific cache line. This situation is noteworthy when one core is actively involved in frequent write operations, while other cores engage in less frequent reads. In this example, addresses A, B, C, and D share the same cache line, but are modified by different cores in distinct log sections depicting false sharing. Messi in this scenario invalidates the cache line when one core stores in its critical section, causing cache misses for other cores trying to access it. This leads to ping-ponging cache lines, resulting in many cache misses and network requests, thus increasing the execution time. Conversely, dance outperforms Messi in false sharing situation. In the case of dance, stores performed by different cores to the cache line would see a cache hit since the cache line is already present in the cache. At the log release date, since only the dirty words of the cache line are written back, the memory would be correctly updated with all the latest updates to that cache line. One could argue adding false sharing support to Messi. However, it introduces significant complexity to the protocol, so that's why we did not try that. Self-invalidation protocols tend to do unnecessary self-invalidations while executing the critical section. As discussed in previous slides, dance proposes two mechanisms to reduce false self-invalidations. However, there is a potential for false and self-invalidation in dance. Consider the scenario given here. We have core 1, 2, 3 trying to acquire log L. Suppose the order of log acquisition is core 1, followed by core 2, core 3, and then again core 1. We'll find that load A in core 1 during its second log acquisition will be a miss in the case of dance, unlike the hit in Messi. It's a miss in dance because previous write signature will have core 2's ID on core 1's second acquire, and core 1 would have updated the Bloom filter signature to address A when it's first acquired the log L. Thus, the second time when it acquires the log, it finds address A in the Bloom filter signature and assumes that cache line that it was stale. Then it self-invalidates the cache line, leading to a cache miss. However, in the case of Messi, this cache line would have remained in the shared state, thus a hit.
In conclusion, directory-based Messi-like protocols in distributed shared memory systems prevent challenges due to high hardware complexity for keeping up with the directory state bits and increased network traffic because of the writer-initiated invalidations. Self-invalidation protocols offer a simpler hardware implementation. However, too conservative self-invalidation during every lock acquisition may result in a lot of needless self-invalidation and other performance costs due to that. So for our project, we aim to build self-invalidation architecture for distributed memory system while solving these challenges. The low complexity self-invalidation protocol that dense architecture offers minimizes false sharing and the unnecessary self-invalidation while suppressing messy in specific scenarios. On top of that, we propose centralized lock management in Dance, which is very effective scheme for distributed locks with the minimal message passing and reducing overhead of the lock manager overall. Thank you for listening to our presentation, and this is end of our Dance. Thank you.